So I'm going to talk about quantum circuit and the hierarchy of many-body entanglement, and in terms of what ultra means, ultra quantum. So this is, let me say a little bit. This is a Simon's collaboration. I'm part of the collaboration, and we have like maybe 14 people together. And by ultra, I think one way we try to explain it is highly entangled. I think that's probably exactly the kind of quantum topic that's being, at least part of it, being studied here, right? So I'm very excited to share what we're thinking about with you. So I'll try to start more broadly and talk about the background, but the new part, the new result that is actually just coming out. So we posted one paper yesterday, and I think we're posting another one today. And in the middle one, we already posted that earlier this year. So these are the new results that I'm going to talk about. And the key word here is sequential quantum circuit. And we didn't invent that name. That name has already been used in various contexts, and including by people here. So we're very much building on the inspirations that we get from all these previous works. And this is collaboration with all my nice collaborators down here. Xie Chen, Zongyuan are students in my group, and David is a joint postdoc between me and Mike at Boulder. Mike at Boulder. So David, I understand, is an alumni from here. And Nat, Robin, and Arpit are postdocs in my group, and Jingyu is a visiting student. So I'll tell you about how we think of sequential quantum circuit as a way to map between anything that's gapped, including all the gap faces in a particular dimension, and also gapped features. I'll explain what features mean. Gap defects or gapped additions to a higher dimensional book. So the first paper, which was posted yesterday, it should show up very soon. This is about using sequential quantum circuit as a way to map between gap faces. And the second paper is about using sequential quantum circuit as a way to do renormalization transformation for certain fracton models. So fracton is a big topic that I work on in the past several years. Although I will not focus on that in this talk, I'll just mention how sequential quantum circuit is part of the story for fracton. And then finally, we talk about, in the third paper, we talk about how sequential quantum circuit can be used as a way to implement string operator for something called the tertiary string. And I'll briefly explain about these two. Okay, but let me back off and start from the very beginning about the notion of entanglement. And entanglement is arguably the most important feature of quantum system, and it has interested and confused some of the greatest minds in quantum mechanics, including Einstein, Schrödinger, and his cat. So at the beginning, people were very suspicious of this idea of entanglement, and they call it a spooky action at a distance. But through many experiments, I think nowadays the common understanding is that entanglement is there, it's true, and it just represents the kind of quantum correlation that exists beyond what is classically possible. Okay. So the simplest kind of entanglement exists between two parties. So this is Alice and this is Bob, and they share an entangled pair of 0, 0 plus 1, 1. And for two-body entanglement, we have very nice tools to characterize them, or we can calculate something called entanglement entropy. We can use these entangled pairs for teleportation, for quantum games, for quantum money, a lot of things that's interesting. Quantum protocols rely on two-body entanglement, and they even show up in quantum gravity when we talk about wormhole connecting two parts, and this famous equation of ER equals EPR. So the entanglement shows up on, of course, one side of the equation. right? And people have a way, in a sense, to classify two-body entanglement, and one way to establish equivalence relation among entangled pairs is to use the idea of a local unitary plus classical communication, which is saying, okay, Alice and Bob, they're separated very far apart, and if they each hold one part of the entangled qubit, and they can each do operations on their own side, and then they can communicate classically what is the power of this entangled states. And starting from there, we can talk about few body entanglement in a very similar way. We can use this idea, the most general way of talking about their equivalence is in terms of the so-called stochastic local operation and classical communication equivalence, meaning that Alice and Bob or Eve or whoever participating in this many-body game can do stochastic local operation on their own side and then classically communicate between the parties. And it was found that we can now define classes of equivalent resource entangled states that basically provide the same quantum power for any quantum game, quantum communication, or quantum protocol you want to implement among the parties. For example, it was found that two qubits can be entangled in exactly one way, that everything's equivalent to this 0, plus 1, 1. And 3 qubits are entangled in 2 ways. There's this GHZ type of entanglement, which is 0, plus 1, 1. And sorry. And then there's this W state type of entanglement, which goes like 0, 1 plus 0, 1, 0 and 1, 0, 0. Sorry, the last one is 1, 0, 0. Okay, this is the W type. And then going from there, 4 qubits was found to be entangled in 9 ways, and that was already quite an achievement because the problem becomes more and more complicated as the number of qubits increase. Okay. But you can also see that this problem gets more and more complicated to do and basically gets impossible if we have a many-body system, if we try to classify entanglement patterns like that. Why? Because, well, by many-body, we usually mean really, really a lot of bodies, like thousands or millions or even 10 to the 23rd, right? We're literally taking the thermodynamic limit of infinite number of particles. Then if we try to characterize entangled states, there are exponentially many parameters. And we can talk about bipartite entanglement, tripartite entanglement, full-body entanglement. It's basically too many parameters to characterize. But on the other hand, this is very important because a lot of the interesting things we do, apart from simple quantum games, have to involve many-body entanglement. For example, if we really try to characterize the resource that's useful for large-scale quantum computation, we need many, many qubits, right? We don't just need 2, we need maybe thousands or even more qubits. And then if we try to understand, if people try to understand quantum gravity, eventually they're talking about a big quantum system that's making, for example, a black hole, and the black hole is evaporating, and how the entanglement changes between those quantum systems. That has to involve many-body entanglement. And finally, which is the focus of my talk today, in terms of understanding quantum phases in a condensed matter setting, we think about gap phases, gapless phases, symmetry breaking phases, topological phases, localized phases, thermalizing phases, anything you can think about. And all these condensed matter systems necessarily involve many-body entanglement. Okay. It is also highly useful to think about many-body entanglement because it really reviews the quantum nature of the system, like in a quantum black hole or in a quantum material, that's not really accessible by the usual way we try to probe the system. For example, in condensed matter system, people try to measure conductance, susceptibility, correlation. But entanglement is just a different lens. It lets you see something beyond what is manifested by these normal response measures. And finally, what we're looking for, at least in the context that I am going to talk about, usually we're in a setting where we have a well-defined spatial dimension, and we have a lattice structure to start with. We have discrete lattice, and then local degrees of freedom on those lattice, which potentially can interact locally with each other. It can be spins, it can be electrons, bosons, but we always start from tensor product Hilbert space, and we start from local interaction, and when we try to talk about many-body entanglement, we'll try to look at in a way where there's some local details that's not important. Because from a condensed matter perspective, we're looking at a microscopic material, and we're trying to look for the global, long-range, universal properties. So we're looking for entanglement features also on that scale. That we're looking for global features, entanglement, and we're trying to capture that. So you see that the kind of tool that we use for characterizing two-body entanglement, three-body entanglement, four-body entanglement does not really work here, because those are, if I have a two-body entangled state here, that's probably something that I don't want to emphasize too much if I want to capture the global pattern. But I need some different perspective, different views to describe many-body entanglement. And one very useful way is to say, okay, I have this big system, and let's take a subregion out of it, and then calculate the entanglement entropy of that subregion. Of course, it usually depends on exactly which region you take out and the exact shape of that region, but there's certain more universal feature within that complicated calculation that can tell us a lot about the entanglement structure of the many-body state. For example, we can talk about the so-called volume law, area law, and topological entanglement entropy when we try to calculate entanglement for a subregion. Volume law means that if we calculate the entanglement entropy for this region, it scales with the volume of the region. So the volume gets bigger, the entanglement entropy gets proportionally big. And this usually corresponds to some high energy and thermal state, highly excited states. And the picture, rough picture, associated with this volume law is basically that everything inside is connected to everything outside. And there's roughly an all-to-all entanglement. And if we drop this subregion and try to think about the entanglement pattern in the whole state, then everything's connected to everything, right? Of course, this is very head-waving picture, but pictorially, you can think that there's entanglement all around. And then there's the other extreme, which we say the state has entanglement area law, meaning that if I take a subregion outside the big bulk, then the entanglement will scale with the length of the perimeter of the region. So by area, people mean the surface area of the subregion. So in here, it's the perimeter of the region. And pictorially, you can think that coming from some shorter range entanglement between degrees of freedom, just inside the boundary and just outside the boundary. So the length of the entanglement becomes much shorter, and that's how you can have entanglement just scaling with the length of the boundary or the area of the surface. And those usually show up in low energy states of a local Hamiltonian, like a gap system, the ground state. It satisfies strict area law. And the gapless system, they usually almost satisfy area law with some very mild logarithmic correction. And then finally, localized states, many-body localized states. For example, they also satisfy entanglement area law. And the last piece that I'm going to talk about in terms of entanglement entropy is so-called topological entanglement entropy, which is a secondary correction to the entanglement area law, which is saying that apart from this linear scaling, we also have a constant correction. It's a constant number, which doesn't change with the size of the subregion. And that usually tells us about some topological feature of the state. And the constant correction means that, I think I skipped a slide, sorry. Let me go back. I somehow jumped one slide. Here, okay, sorry. Here, if we drop the subregion and just think about the total entanglement pattern for area law, you can think of it as some short range entanglement all around, throughout the whole system, which is very different from the picture we had for the volume law state. Okay. And then for the entanglement entropy part, for the topological entanglement entropy part, it's a constant correction to the area law. And that usually means that we have certain constraint among the boundary degrees of freedom of the subregion. And that's a hallmark of something topological happening. And that can come from, let's say, gauge symmetry in a gauge theory, or something even more sophisticated than that. And different gamma will characterize different topological order. So volume law, area law, and topological entanglement entropy, that's what we can learn from just calculating the entanglement entropy of a subregion in the total system. Okay. So I like to draw diagrams like this, where, of course, the most general kind of many-body entanglement or volume law, that's the biggest one. And inside, there's a subregion, actually a very small subregion. It should be just this corner, but I made it very big because that's going to be the focus of my talk, which is area law entangled, so the low energy localized part of many-body entangled states. And then within that, we can have gap phases. So these each blue region, they are the gap phases characterized by gamma. Gamma can be zero, that's a non-topological state, or by non-zero gamma, which corresponds to a topological state. But then we know that the structure is more interesting than that, right? Even for example, the same gamma, we can have different gap phases. For example, if we have gamma equal to zero, we can have in transverse field Ising model, we can have symmetric phase, symmetric breaking phase. We can have symmetric protected topological phase. We can have interior quantum Hall. We can have topological states. We can have a lot of things that cannot be fully captured by just calculating entanglement entropy for a subregion. So to get a more detailed lens on many-body entanglement, we need some other tools. But we don't want to look at everything, right? We don't want to look at exponentially many parameters of it. And it turns out that another tool that we can use to look at many-body entanglement is quantum circuit. Okay, so this is what I'm going to talk about, how we use quantum circuit to establish to get more information about many-body entanglement, to somehow establish a structure level of hierarchy among many-body entangled states. Okay, so let me explain what is quantum circuit? Quantum circuit, of course, is this thing that people invented when they try to design quantum circuit to implement certain quantum algorithms. And the way quantum circuit is designed is that it's composed of local quantum gates. Okay, so each of this thing that I draw corresponds to a local unitary transformation. And the quantum circuit is just by putting all these local unitary transformations together. For example, if I have a bunch of qubits, I can apply one layer of unitary gates like that. And when the unitary gates, when they don't overlap, they all commute with each other, so we can implement them all at the same time. So that's one layer of unitary applied everywhere. And then I can apply another layer. So Again, gates in the second layer all commute with each other, but they don't necessarily commute with the gates in the first layer. So we need to stack them up, right? So, but then we do a second layer of local gates. And then we can keep doing that. We can do a third layer and fourth layer. And the number of layer is called the depth of the quantum circuit. I think that's also a measure of how good the quantum computers are, depending on how many depths of circuit you can apply to your qubits. And then there can be, you can imagine that depending on the circuit depths, you can do different things to many-body entangled states. The biggest circuit, and I'm going to talk about, is so-called linear depth circuit. Linear means that the depth of the circuit scales with the size of the system, right? And especially linear size of the system. So if I have let's say a 2D system like that, and it's L by L, then I can have a linear depth circuit where the depth is proportional to L. And if that's the case, then all the degrees of freedom can be connected to every other degrees of freedom because their separation is at most L. So that can generate this all-to-all entanglement and generically give you entanglement volume law. Linear depth circuit corresponds to generating entanglement volume law. So if I back to this picture, the linear depth circuit can take me from this area law region to the high temperature thermal volume law region. Okay, the other extreme is so-called finite depth circuit, where I have layers of circuit, but I only apply a finite number layers of them. Finite means that it's a number that doesn't grow with system size. So as the system gets bigger, the number of layers I apply doesn't increase with system size. So that's what I mean by finite depths. And finite depths has the nice property that if you start, that pretty much everything stays local. In particular, if I start from a local operator and conjugate that by the finite depth quantum circuit, it remains local. Okay, so one body operator might become 5 body, but it's still local, as long as it's a finite depth quantum circuit. So local operator remains local, and short range correlation also remains short range correlation because there's only so much thing you can do with finite depth circuit. And short range entanglement also stay short range entanglement. Basically, I'm saying that if I start with a product state and I apply a finite depth circuit, and the finite depth circuit can only generate short range entanglement, pretty much in that picture, right? You can only entangle close by things, and you can't entangle things that's very far apart.
But if someone had already entangled the outside to whatever long distance, many qubits,
okay,
then you would generate a long, not a short range, but a long range entanglement, wouldn't you?
You mean if these qubits are already entangled from something else?
Yeah, from someone else. Yeah, exactly.
Yeah, yeah, that could be. Yeah, like you can teleport. you can do something locally here and try to teleport that entanglement to somewhere else. So
but I mean, then the entanglement would not stay local, but it would distribute very rapidly. Depends on what happens.
Yeah,
depends on the initial state, no?
Yeah. So here I'm just starting from pure product state, and no connection to the outside whatsoever. Just everything's product state to start with.
So assume everything starts in the product state to begin with.
Yes. I'm just starting from this very simple starting. Another situation is where I start from something inside a gap phase, so as the ground state of a gap phase, but not connected to the outside. So it's just an isolated system that's entangled with itself, but as the gap ground state of a gap system, then finite depth circuit can change short range entangled structure, can add entangled pairs locally or remove entangled pairs locally, but it cannot change the long-range entanglement. So in a sense, it cannot change the topological feature. For example, it cannot change the gamma that characterize topological order. So finite depth circuit is in a sense very safe, but also kind of boring. Right? It will take you into different phases, but you're guaranteed that you always stay within the same phase. Okay, so just you get some different entangled state, but that entangled state stays within the same gap phase. So this diagram, we had the linear depth circuit, which can take you from inside the area law region to the volume law region. But then the finite depth circuit only maps within each gap phase. It establishes an equivalence relation among wave function of the same gap phase. And now we're asking an interesting question, the next question. What if I want to jump between all these gap phases? Okay. Let's say we want to focus on the gap part of the phase diagram for now, but already there are many interesting gap phases that we know about, like symmetry breaking phase, topological phase, SPT phase, fracton phase. We already have a bunch of them to play with. So let's ask, how do we map from one gap phase to another gap phase? Obviously, finite depth circuit doesn't do that. Finite depth circuit is how we define equivalence relation within a phase, right? So it won't help us jump between phases. We need something more to jump between phases. And it was proven already. This is almost 17 years ago. People already knew that in order to map between some of the interesting phases, for example, the product state to the symmetry breaking phase, or the product state to toric topological phases, we need at least a linear depth circuit. And it's proven that the linear depth is the lower bound. You cannot do better than that. You can try to achieve that, but you cannot do better than linear depth circuit. Oh, sorry. On the other hand, generic linear depth circuit is too powerful because generic linear depth circuit takes you from inside to way outside to volume law, right? So generic linear depth circuit is not what we are looking for. If we just want to jump between, characterize the entanglement difference between different gap phases, then generic linear depth circuit is not the answer. So we're looking for a subset of linear depth circuit that does just the job of mapping between gap phases. And the answer, as already advertised, is this idea of sequential linear depth circuit. Okay, so let me try to explain what is a sequential linear depth circuit. Well, let me first try to illustrate that with some example. And these simple examples, as I said, we didn't first write it down. It already showed up in previous works, and maybe even more. So if I miss any reference, please let me know. Okay. So let me just start from the simplest example where we have the Ising model. And we start from the the symmetric part of the Ising model to the symmetry breaking part of the Ising model. And let's say we want to map between the two extremes. So in the symmetric limit, the ground state wave function is the plus state as a product of them. And in the symmetry breaking limit, the wave function is the cat state, is the GHZ state, right? All 0 plus all 1. And the global symmetry is spin flip, 0 to 1, 1 to 0. This is the global symmetry. So the all plus state is symmetric, and the GHZ state is symmetry breaking. And according to the proof by Sergey, Matt, and Frank, is that we need a linear depth circuit to map between the two. Even though this looks like very simple wave functions, but we need a linear depth circuit to map between them, basically because the GHZ state has a long-range correlation, while the product state doesn't have it. Okay. So you need a linear depth circuit to establish long-range correlation throughout the whole system. The long-range correlation, of course, measured by the correlation function of the autoparameter, which is a single z. Okay, and this is one possible formulation of the circuit. This is what we have in our paper. It might be slightly different from what previous papers have, but they're all equivalent. Okay. So the way we do the circuit is to do something called Rx, where Rx is e to the minus I pi over 4 of x, so pi over 4 rotation with a sigma x. And now we do a pi over 4 rotation with ZZ. So these are all Pauli generators. We use them to do pi over 4 rotation. We first do x and ZZ and x, ZZ and x and ZZ. So when I use the blue box to box together the unitary, each of the blue box correspond to a two-body unitary. So that corresponds to like the gate I was drawing. So this is two-body unitary, two-body unitary, two-body unitary. And then you can see why we're calling it sequential, because we're acting on qubit 1, 2, 2, 3, 3, 4, and we move along the chain. And eventually we cover the whole system and map from the all plus state to the GHZ state. This is one example of what we call a sequential quantum circuit. Okay, and if you trust me, or if you do the algebra, you will see that an X operator in the middle of the chain gets mapped to ZZ, and the ZZ operator gets mapped to X. So this actually implements the Kramer-Vanier duality of the model and maps from symmetric phase to symmetry breaking phase, or the symmetry breaking phase back to symmetric phase. And you can see that this is a circuit that has steps L, because it's a ladder structure, it keeps going, and then eventually you need L layer to implement the whole circuit. But each layer only acts on 2 qubits. And then another very important feature of this circuit is that it doesn't preserve locality, because you can look at how the circuit acts on, let's say, X on the first qubit, probably X on the first qubit, and that gets mapped to a very non-local operator. And that's somehow one of hallmark of these non-trivial sequential quantum circuit. They don't preserve locality. Yes, is that a question?
What tells you that you have to consider this GHZ state instead of, I mean, I could take any of the ferromagnetic states, and if I take the product state of all zeros, then there's a trivial circuit, right?
Question. Yes, so one thing I didn't emphasize, I should have, is that we want the circuit to preserve the global symmetry, because otherwise we're basically breaking the symmetry and then there's no difference, like you said. And we don't even have to go through a phase transition to go from all plus to all zero. So we want to preserve the global symmetry. We want the circuit to, in each step, to preserve the global symmetry. And you can see that we're doing that because all the generators are symmetric. So this is explicitly symmetry preserving. And if we want to do that, we can only map the all plus state to this symmetrized state, right? Otherwise, we're not preserving symmetry. Yeah, and because of that, we have to do this sequentially, and we have to do it in a linear depth. Yeah, thank you. And this circuit doesn't preserve locality. Okay, so this is the first example. The second example is the circuit maps from a trivial state to the toric code. Okay, so this is trivial to topological. So let's say the trivial state is Hamiltonian and sigma z on all the edges. So every qubit we put it in state 0 with the Hamiltonian term being a single z. And then for the toric code, we just take the usual Poincare term and vertex term, and then that's the toric code. And the trivial state, of course, has 0 topological entanglement entropy, while for toric code, it has non-trivial topological entanglement. And this has been a circuit of the sequential kind, has been discussed in this paper. And let me try to, actually the version I'm presenting here may be slightly different, but they're again equivalent in terms of their ability to map between phases. But let me try to present what we have in our paper. And so we are using, again, this pi over 4 rotation, the pi over 4 rotation generated by a single Z, followed by pi over 4 rotation generated by the plaquette. The AP is the plaquette operator. So diagrammatically, I'm drawing these dumbbell-shaped thing to represent this kind of gate. So the Z part is acting on this edge, and the A part is acting on the whole plaquette. So the first step is to apply this particular gate set to all the plaquettes in the same row. And you can check that the gates in different plaquettes, they commute with each other. So they can all be implemented in one step. Okay. And then we're done with the first row. And we move on to the second row. In the second row, again, all the gate sets commute with each other, and we can apply them in the same step. But the gates in the second row doesn't commute with that in the first row. So we have to do the first row, and then do the second row, and then do the third row, and from there. Okay. And eventually, if we try to close up the system into a periodic boundary condition, then we actually have to do it sidewise. We have to do it like this gate, this gate, this gate, and then we're done. Okay. So this is a circuit of depths that scales with Lx plus Ly. This goes with linear size in both directions. And it is non-local. For example, if you keep track of how this Z operator maps, it maps to a string of Z, and this is basically how we get the non-trivial string operator for toric code, right? And we can change the ground state degeneracy of the model exactly because of this non-locality preserving property of the Hamiltonian. Okay. Oh, and let me add a more comment that this is called sequential because we're doing first row, second row, third row, and then 1, 2, 3 in the last row, we're doing according to some sequence. So this is called a sequential circuit. So more generally, by sequential circuit, and again, we didn't invent this term has been used pretty broadly in the literature in terms of generating quantum states using quantum circuit, and also implementing in terms of, let's say, matrix product state, tensor product states. And there are different ways you can imagine that the sequence goes, right? In 1D, you can go from left to right. In 2D, we can do patch by patch, and then eventually have a quadratic depth, or we can do row by row and have a linear depth, or we can do radially inside outward. You have two different patterns. So all of these are called sequential circuit, but the way we try to give a more systematic definition is that we say that sequential quantum, the sequential, so pictorially, you see that this is some sequential application of either local unitary or finite depth quantum circuit. So in the 1D case, it's a sequential application of local unitary, but in the 2D case, we can have a sequential application of finite depth circuit in some region, subregion of the system. And then generically, it has linear depths or quadratic depths or something, unless all the gates commute with each other, of course. But then one crucial common property of these kind of circuit is that if you look at it, each local degrees of freedom only gets acted upon by a finite number of gates. And that's very important because we can deduce from there that the total number of gates will scale with the volume of the system. And then even though the circuit doesn't preserve locality, it doesn't preserve short-range correlation, it doesn't preserve short-range entanglement, it does preserve entanglement area law. Okay, that's the key property, that sequential quantum circuit is chosen, is designed in a way that it doesn't preserve a lot of things, but it preserves entanglement area law, and using the folklore between entanglement area law and the gap, which is, of course, hard to prove in higher dimension, but if we take that folklore, we'll say that sequential quantum circuit preserves the gap of the ground state of the Hamiltonian, the parent Hamiltonian of the wave function. So let me try to give you a very simple illustration of how sequential quantum circuit preserves entanglement area law. Just imagine it's one-dimensional case where we have this very case structure of the circuit, and you can see that each degree of freedom gets acted upon by only two gates. And generally, we can have any finite number of gates acting on each local degree of freedom. And then if we take a local region and look at the gate acting across the boundary of the region, here it's just this gate here and that gate up there. So those gates can increase the entanglement, but it will not increase the entanglement beyond area law. Right? Here it's just increasing entanglement by a finite amount, but if you have a higher dimensional system, it can change the pre-parameter in the area law term, but it will still have an area. So that's why sequential quantum circuit is safe. It keeps you inside the gap region, but it can do interesting things by mapping from one gap region to another gap region. Okay, so this is what we try to show in the paper, that we can basically use sequential quantum circuit to map between all kinds of gap phases that we know about, basically everything that we can think about. For example, we can map between trivial phase and symmetry breaking phase, which I just showed you, and we can map to symmetry protected topological states. All the examples we can, all the group cohomology ones and even beyond group cohomology ones. And then we can map to those fractional topological states like toric code and string net. Of course, these have been written before. And then we can go to even higher dimensional topological states like 3+1 topological states and their generalization like Walker-Wall model, Digraph-Witten gauge theories. And finally, we can map to fractons. So we basically try to do this exhaustively. We can't prove that it can do everything, but we show by just exhaustive effort that we can design circuit that will allow us to map between all these gap states. Okay, so of course we take one fixed point wave function from each phase and try to map between them, and all the other states within the phase can be reached by another finite depth quantum circuit. So that's what we did in the paper. Okay. So then we know what these red arrows correspond to, right? So if we want to state the white arrows of finite depth circuit keeps us within each gap phase. The red arrows of sequential quantum circuit takes us between gap phases, and then the linear depth circuit, generic linear depth circuit, will take us from area law into volume law. And we have a strict containment relation from finite depth circuit to sequential quantum circuit and to linear depth circuit. So each of them is strictly stronger than the former. And if we try to compare them in terms of what is being preserved and what is not, we see very clear distinction. So finite depth circuit pretty much preserves everything. It preserves entanglement area law, locality, correlation, and short-range entanglement. Everything preserves. So it's a boring pack. Sequential quantum circuit preserves area law, but nothing else. It doesn't preserve locality. It doesn't preserve short-range correlation or short-range entanglement. So it's more interesting, but also keep you within the gap region. Okay. While the linear depth circuit doesn't preserve anything. It's totally wild. It can create even a chaos or something. Yeah. Okay. So this is what we show among the three papers. In the first paper, that sequential quantum circuit can act as map between gap phases in any dimension with any symmetry, with any topological order. We show that we can do it. And then the other two papers that I mentioned, which I'll only be able to very briefly tell you what they're about, but I'll try to give you a taste of what they're like. We're trying to use sequential quantum circuit to generate gap features in higher dimensional bulk. So So in one of the paper, we're using sequential quantum circuit to add layers as a renormalization step in fractal models. I know there are lots of big words. I won't do any justice to this topic because usually when I give talk on fracton, I'll spend the whole talk on fracton, but that's what I've been doing in the past 6 years, and I think I'll talk about something new. So I'll shrink this fracton part to just like 2 minutes, but if you want more details, I'll be very happy to talk to you afterwards. And otherwise, we have another paper, which hopefully will be posted today. It's about generating defects in topological phases. And in particular, we talk about generating the so-called Cheshire charge defects in topological physics. This name came from 1990 by people in high energy. They talk about non-abelian gauge theory, and they come up with this fancy name of Cheshire string on Alice loop. Sorry, Cheshire charge on Alice string, making reference to Alice in Wonderland, that there's some cat that's sometimes there, sometimes not there. And I'll also only be able to very briefly tell you what this is about. And again, if you're interested, happy to elaborate later. Okay, fracton. So fracton is is a very new topic. The word got invented around 2016 or something, but it basically describes a bunch of very exotic models, strongly correlated exotic models that contains fractional point excitation, which doesn't quite move, which is surprising because usually we think of, let's say, insulators. If you excite an electron from the conduction band to the valence band, as you excite them, they can move, right? They can move with momentum, with energy. But in fractal model, you can also have gap excitations, but somehow, due to some fundamental constraint of the strong correlation, the gap excitation just does not move on itself. Okay, and people have come up with different ways to explain why that happens. And another closely associated phenomena is that these models have very big ground state degeneracy, and they're stable, extensive ground state degeneracy. And the ground state degeneracy usually goes as exponential in the linear size of the system, so exponential in L. This is pretty big. And this is usually related to something called subsystem symmetry, and because of the restricted dynamics of restricted motion of the fractional excitation, this leads to very slow dynamics. So there are a lot of topics associated with fractons, and as I said, I can't do any justice to that. But I'll just talk about one aspect that we have been focusing on in my study, in my groups of study of fractal models, which is how to perform a renormalization transformation for these fractal models. Because you see that it has the very weird property that the ground state degeneracy changes exponentially with system size, which means that when you try to just increase the system size, even the ground state degeneracy will change. And that usually doesn't happen in the normal kind of order that we see, either topological or non-topological. Change ground state degeneracy just by changing the system size. But for fractal model, we need to deal with that. And it shows up in some of these type 1 fractal models. If any of these make these names ring a bell to you, great. If they don't, then don't worry about them. I'm just throwing them around. And then what we are proposing is that for these set of models, if we try to increase or decrease the system size by 1 in one direction, for example, if we try to change the size by 1 in the z direction, what we need to do is to use sequential quantum circuit inside the plane. We apply the sequential quantum circuit in plane that has depths that scales with the linear depth, linear size of the plane, Lx plus Ly, no Lz dependence. Okay, so in plane sequential quantum circuit, and it only acts near the plane. And by doing that, we can change the ground state degeneracy. We can change the excitation type around that plane, and effectively shrink the system size by 1. Okay, you can change ion types and statistics. and anything related to that plane, because all these are non-trivial gap features associated with that plane. Okay, and change the quantity degeneracy. And as I said, promised, I'll talk a little bit more about defects in higher dimensional topological phases, and this is in terms of 3+1D topological phases. So 3+1D toric code, which is only slightly more complicated than 2+1D toric code. Right? It's a stabilizer model, exactly solvable, and we thought we know everything about it. And we know that there's a point excitation. If you think of it as a gauge theory, that's the gauge charge. And there's a flux loop excitation, it's the flux of the gauge theory. And the charge can be either boson or fermion. It's 3 dimensions, so it's more boring. There's no anion. The point excitation are either boson or fermion. And then the charge flux can have a runoff bomb effect, braiding around them. But somehow, starting from at some point, people start to talk about defects in topological phases. And I cannot fully explain why this is something people are interested. And I'm only recently starting to understand for myself why this is important. Because somehow this is related to something very deep mathematically, which is called the higher category description of higher dimensional topological order. Even though we thought we understand everything about 3+1D toric code, mathematicians say, no, you don't. That you really need this higher category theory, and you're missing something in the bulk. And it turns out what we're missing in the bulk are these defects. And the defects are the so-called Cheshire string. And they're basically charge condensate of the E particle along the defect line. Okay? And so if you bring a charge to the defect, it disappears. Well, how can it disappear? Because it's basically going into the degenerate state of the condensate. This is what people call descendant excitation. It's a gap defect, and it's related to higher category theory, which I'm not going to explain. But since it's gapped, I can use sequential quantum circuit to study them. So basically what is happening is that, remember I showed you how to generate GHZ state in a one-dimensional chain? We can still do that here, except that we're doing it inside a 3-dimensional bulk. Let's say we have a 3-dimensional paramagnet of all the plus state. We just take one small 1D defect out of it and turn that subregion into the GHZ state. Okay, we can do that. And we know that that is done by a sequential quantum circuit. And then the one step that takes us to the Cheshire string in topological phase is just to turn that circuit by coupling to gauge field. And then it's just the correspondence of language. And then we say that this GHZ state is actually correspond to the Higgs phase of the gauge theory. And it's a Higgs defect inside a topological bulk, and that is generated with a sequential quantum circuit. So basically what we're trying to do is try to talk about these defects also in a language with unitary circuit. And the good thing with unitary circuit is that then we can talk about how to move these defects, how to deform them, and how to fuse them with the hope that eventually this will let us understand what are the higher category mathematical thing talking about for these topological things. I don't think anybody fully understands that yet, but there are mathematical indication that this is the right way to go. And for me, I'm just trying to understand that. And with the sequential circuit language, it makes me feel better that eventually I'll be able to understand it. Okay, and that's all. That's all I want to say. Basically, I showed you how different quantum circuit can give us different hierarchy among many-body entangled state. The finite depth circuit is most boring. The sequential quantum circuit does something more interesting, while the linear depth circuit does something totally wild. And I compared how what they preserve, what they don't preserve in terms of the gap features. And then finally, I also very briefly talk about how we use them to think about either defects or renormalization step for higher dimensional states. Okay, and there are many, many open questions. For example, one thing I didn't mention is quantum circuit for chiral phases. That we're working on it. We have some idea, but I don't want to talk about it. But if you are interested, we can talk maybe later. And then quantum circuit for gapless phases. What kind of circuit will take us to the gapless region, but not all the way to volume law, right? Obviously, we need something that's beyond sequential circuit, but maybe not too much beyond. We just need a logarithmic correction. But what kind of circuit gives us logarithmic correction, but not more than that? And then, obviously, there are more hierarchy levels between sequential quantum circuit and linear depth circuit. This is an example that David showed me, where he said, "Oh, you just take a MPS and you kind of fold it, right? You fold 1, 2, 3, 4, 5, 6, 7, 8 on top of 1, 2, 3, 4. And then you can see that the entanglement kind of gets doubled. So area law still stay area law, but it kind of gets squared. So it's still finite, but it gets squared. And this cannot be done with a sequential quantum circuit. This has to be done with something more. But this is also not all the way to linear depth circuit. This is still keeping area law as area law. So obviously there are more structures out there that we don't even know. And finally, we're very, very interested to look at the matrix product operator, tensor product operator representation of all the circuit and how, let's say, given a matrix product unitary operator, how do we see that it's a sequential circuit? And what kind of sequential operation does it do? Yeah, those are very interesting questions. Thank you.
Any questions? I'm not sure if I understand all the details because I'm a simple-minded experimentalist. So would that be an example of a non-sequential?
Yeah. Because
I was all the time I was wondering what is non-sequential? Because the circuits that we usually have in the lab are sequential.
Right.
And this would be a non-sequential.
Yeah, we define sequential.
This folding, right?
But this folding can be achieved by some permutation, by some movement of the qubits, basically. But we define sequential to be that each local degrees of freedom only gets acted upon by a finite number of gates. So it doesn't really depend on what pattern you're using to implement the gates. But as long as you apply a finite number of gates for each qubit, that's what we define as sequential. And because of that, you can only multiply.
Non-sequential then would mean not a finite number of gates, or what?
Yeah, the total number of gates can, in general, scale with the volume of the system. Like in the Wendy staircase example, the number of gates is linear.
So because these are 2 qubit gates, not
yeah, they're 2 qubit gates.
So it scales like the volume. Yeah.
Excuse me?
It scales like the volume.
It scales like the volume. Yes. Yeah,
so I'm still not sure if I understand the non-sequential.
A non-sequential would be like a generic linear depth circuit, right? A generic linear depth circuit, so you just do one layer of unitary, another layer, and many layers that scales with the system size. That would be non-sequential. I know it's still you still implement it in a time-wise. Yeah. I guess the word is a little bit confusing in that sense.
I guess is it that in this example, if you look at the single qubit.
This is the example. No?
Yeah, but if you look at the single qubit, the number of swap gates you have to apply to it is scales with the length of this.
Sorry,
is that the reason this is non-sequential?
Oh, this one
is because when you look at the single qubit, if you implement this with swap gates, the number of swap gates scales with the length of this line. Right?
Yeah.
And it's not a constant number.
It's not a constant number. That's just how we define. I guess
scales more favorable because you have the swaps.
You have to do more swaps. You have to do a linear number of swaps on each qubit.
Yeah, you kind of have to swap
So,
for all the way to the end. That's like a linear number of swaps. But so sorry. I guess I guess you're saying that when we apply gates, we always apply one after another, and that's the time sequence. Exactly. So that's just we use this word because it has been used to describe generation of, let's say, matrix product states by local gates one by one, in tensor product states local patch by local patch. So in that sense, it's sequential in terms of local by local sets. So that's what we mean by sequential here. And this is already being used to some extent. So yeah, I know it's a little bit confusing if you just say everything is sequential.
So slightly related to this, so I'm trying to connect this to basically quantum states that we see in analog quantum simulators. And there I can use the same language, right, of like area law, volume law, states, and so on. But where the language really differs is in the description of the circuit or the dynamics that I can use, right? And in particular, in analog quantum simulation, often has the case that you actually have many gates acting at the same time simultaneously, and also basically acting on all pairs simultaneously, right? So then it's not so even anymore, so not so simple anymore to actually count gates, right, or to specify the depth of the circuit.
Well, so in that sense, it's just the time you spend doing time evolution. That's the depth. So there's a kind of a correspondence between the depth of the circuit and the time of Hamiltonian evolution. Yes.
And then okay, so then you just count basically the time by basically how often how many coupling times you have your Hamiltonian on for.
Exactly. Yes. Yeah. So they're more or less equivalent. I would say 99% of the time you can think of them as equivalent. There's some tiny detail that I don't want to explain here, but pretty much they're the same.
I see. So this distinction between sequential and non-sequential, or finite depth and sequential circuits should be the same.
No. I'm saying that you can think of, let's say, finite depth circuit as evolving a Hamiltonian for finite time, and linear depth circuit as evolving Hamiltonian for linear time. But sequential circuit is slightly different because sequential circuit has this structure that you're doing subregion by subregion by subregion. So it's like you turn on the Hamiltonian here for finite time, then the Hamiltonian here for finite time, then Hamiltonian here. So you sequentially turn on the Hamiltonian for finite time.
I see.
Yeah.
Yeah, thank you.
I have a question regarding the degeneracy of the ground state. So I have two phases which has different degeneracy, and what happened if I map like the higher degeneracy ground state to the other part? Does it map? It cannot be mapped into the same ground state.
Oh yeah. So exactly. So like I showed that. Okay, let me try to find the page. Basically, some of the local operators get mapped to the non-local string operators in the topological phase. So here, so that the degeneracy associated with the non-local string operator, you can trace it back to this qubit. So this qubit, if you change it initially, you will end up with different logical states.
So it might not be the ground state, but the local.
Well, depending on what Hamiltonian you choose for this qubit. If you change the Hamiltonian of that qubit, you can end up in different ground state.
And my second question is that so there's like these work of like measurement assisted feed-forward kind of approach that you can fold like kind of linear depth circuit down to constant depths.
Yeah.
Do you think this will be workable for all the cases that you for mapping between different phases?
Yeah,
sequential circuit?
That would be something interesting to see. From what I understand, measurement, for example, in terms of generating non-chiral topological order, they can generate things like solvable groups of gauge theory, for example. You cannot generate like double Fibonacci kind of topological. So there's some more weird type of topological order that cannot be generated with finite depths of measurement and then correction. But for our circuit, we can do them, all of them, with sequential quantum circuit.
So there are certain cases that's not kind of reducible. Or
yeah, it turns out. So these are all very interesting questions because different quantum platform, as I understand, they're better at different things. Some of them are better at measurements. Some of them are better at unitaries. Some of them are better at having ancillars. And you can ask, given these subset of resources, what's the most efficient way to generate certain states? Right?
So I have a question, like, maybe I didn't follow closely. So when you say sequential circuit preserve the gap, is it a rigorous statement or?
Okay, the rigorous part is that it preserves entanglement area law.
Yes.
And the non-rigorous part is entanglement area law implies gap.
I see.
But this is what I would like to learn from you, more in more detail.
Okay.
What you just said. What is the relationship between the exact? I mean, you can explain very well. So that's why I'm asking. What is the exact relationship between having a gap and the entanglement?
Well, I think in 1D it's proven that entanglement area law implies the existence of a gap in the parent Hamiltonian.
Why?
Hastings proved it, is that right? Or
Somebody has proved. Yeah, I know you mentioned it, but.
Yeah, so it's quite amazing that they're able to prove it. I cannot prove it.
But what is the essence or the physics or what's behind it? Is it easy to? Maybe it's not easy to explain. If you can't explain it, maybe nobody can.
I don't remember all the details of the proof. I think the.
No, I'm not going through the details of the proofs. Just a general idea.
Well, if you ask a few theorists, they would say, okay, space and time are equal. Well, sorry, I'm maybe getting too ahead of myself. But I guess just from our experience, we see that all of the gap states we see have entanglement area law. That people have done calculations, and I guess that's what we see in the conjecture is that
Gap systems have an entanglement
area law, yes. Entanglement area law. And then the conjecture is that entanglement area law also implies the existence of a gap. And in one dimension, I forgot exactly how the proof went.
I don't remember. It's this result by Hastings, but I think basically Hastings showed this in one dimension.
Yeah, she mentioned it.
Yeah, so I think somehow there's a relationship between area laws and clustering of correlations and having a gap or something.
Yeah, somehow.
They're all the same somehow in 1D, but I also don't know. It's a complicated proof.
In 2 dimension, it's more obscure, right? I mean, like it's there are explicit examples where you have gapless states in 2 dimensions and they follow area law.
Yeah.
You also mentioned some, like probably some text in your slides that the simplest one, maybe fine-tuned examples, but there are infinitely many fine-tuned examples that have this because you can always like take just any thermal states, partition functions, and turn into 2-dimensional ground states. They would most likely correspond to some gapless, ground states. And these will have area law, but then the gap is unlikely to be the system is unlikely to be gapped because of the lack of mass.
Exactly, that's why higher dimensions are hard to prove.
Yeah.
If you want to, even if you want to prove it, you might need to add something.
Yeah. So you're saying basically this is like a rule of thumb that you're trying to
yeah.
Okay, I see. Okay, thanks.
Generically.
I see.
Can I ask some more basic questions about this fracton? So,
Okay.
I'm wondering about the because of this exponential gap degeneracy. Can one say something about gap stability, or is it just? There's no.
That's a good point, and the fact that people talk about it so much is because the gap is stable to any local perturbation.
That's no.
Yeah, because all the logical operators are global string or membrane operators or fractal operators, or whatever is of global distance. So no local perturbation can split the degeneracy.
But in your consideration, that's, I mean, the gap stability not directly, you don't need it in some sense, or I guess otherwise you don't have a well-defined phase, or.
Yeah. If the gap is not stable, then we just
Then you can just
split it and then talk about
Quick question, follow my previous question. So if you suppose you start from certain maybe trivial states with certain parent Hamiltonian, and then you do such sequential mapping, right? I mean, it's intuitive that, at least for me, like if you just look at the state level, I mean, after the sequential mapping, you've got a state which has error law, so it's guaranteed to have at least one parent Hamiltonian. Right? But the choice of parent Hamiltonian is not unique. So let's suppose you start with certain trivial states which has some interesting physical Hamiltonian, but then you apply the sequential mapping, you just follow this original parent Hamiltonian, then the mapped parent Hamiltonian is not necessarily local, right? At least it's not obvious to be local.
Yeah.
But then if you start from the states, there is a different, maybe potentially different parent Hamiltonian which is local. So you're saying like, are these two related somehow, or how do we interpret this physically?
Yeah, very interesting. I mean, you're exactly correct that if you just keep track of how the original local terms evolve under the Hamiltonian, in a lot of cases. So I showed you where the single term maps to a string operator, but it's even more than that. There are other terms that maps to product of local terms and become non-local.
Yeah.
And so eventually for simple cases like this is stabilizer. So you just need to get one set of generator for the stabilizer. It doesn't have to be all local. But eventually well, since we know them all local, we know how to choose a local set of generators out of the non-local set of generators. But yeah, if you ask me in general, if I didn't know what Hamiltonian I'm looking for, and it doesn't have a group structure, then if I end up with a bunch of non-local operators, how do I get a local Hamiltonian out of it? I'm just waving my head here. I'm just saying, okay, it's gap, so we should have a gap. Oh, sorry, it's area law, so it should have a gap Hamiltonian.
Yeah.
But that's a great question.
So you sort of stopped at linear depth circuits, but there's, I mean, you can go beyond, right? Most generic quantum states require exponentially deep circuits to prepare. Is there anything interesting you can say beyond linear depth circuits, or is there a reason why that's not interesting?
No. I don't have a reason. Just that in my very naive mind, volume law is the most I can think about. But I think if for people talking about like black hole complexity associated with that, yeah, they talk about even evolution after. I don't know, but I can imagine a situation where even beyond linear depth circuit can become interesting. So, in a condensed matter sense, I'm not exactly sure in what kind of setup that would be. But that's just probably because of my own ignorance. Indeed, you can keep evolving until reoccurrence, right? And then everything comes back.
That's exactly my last question I had, because from a computational point of view, it seems clear it would be interesting, but I can't think of any setting in condensed matter, but maybe.
It would be interesting to have an even bigger circle. Yeah.
Maybe we can thank Xie again for this beautiful talk. She will be around a bit more if I understand correctly. Yes, so use the opportunity to talk to her.